I find it so fascinating how humans learn. Like, we don't need to be explicitly told what to do, but we just do it. And then over time, as we get feedback, we learn and iterate and get better at whatever we're doing. For example, think of a child who's trying to ride a bike for the first time. At first, they probably won't do so well. They'll lose their balance. They won't get too far. But over time, they'll learn and they'll figure out what specific movements they need to do to balance the bike. People for decades have thought, how can we make machines learn the same way? And now finally, we have this really cool thing called reinforcement learning, which is able to do exactly that. Back in 2016, Deepmind made an algorithm named AlphaZero. It was an algorithm that played the game of Go, and it was able to beat Lee Sedol, one of the best Go players in the world. Now, Go isn't just any game. It's considered the most complex classical board game. In fact, just to give a sense of how complicated it is, there are more possible board positions of Go than there are atoms in the universe. Like, that's how crazy complicated the game is. But AlphaZero used a lot of game-specific heuristics, and it learned from expert-level games. But then recently, Deepmind released another paper with a new algorithm named AlphaZero. This new algorithm not only learned entirely from self-play, but it was also able to generalize to Go, chess, and shogi, and achieve superhuman performance at all three games. So here in this video, I'll be explaining exactly how the algorithm works. So of course, Deepmind used a deep neural network for this algorithm. But it's not just any neural network, it's a network made up of 19 residual blocks with skip connections in between. Now these skip connections are really important because they allow the gradient to pass all the way to the first couple layers. Another special thing about this neural network is that it has two outputs, a policy vector and a value. So a policy vector is a vector which contains the probability of taking a certain action in that state. And the value function outputs a value between 1 and -1. And it's basically the network's prediction of which player will win from that state. Okay, so to actually train our model, we have it play against itself. It then collects experience, and we use this experience to train the model. Okay, so when the model is playing against itself, in order to decide which move it's going to take, it uses a technique called Monte Carlo tree search. The tree search starts off at a root node. This is the current state of the board. Then the model looks at all of the possible actions it can take from that state, and it computes the upper confidence bound of all of these actions. So the upper confidence bound is computed by taking the expected value of this state action pair and then adding this upper confidence bound term. This term basically looks at how many times this state has been visited. So we take the square root of that and then divide it by how many times this state action pair has been visited. So the less a state action pair has been visited, the higher this number will be. So the higher the upper confidence bound of that state action pair will be. This term is just a hyperparameter that we can tune. The higher this number is, the more exploration. And this is the original estimation of the probabilities that the neural network estimated for the state action pair. The network then takes the action with the highest upper confidence bound. So after taking this action, if the next state is not a leaf state or a terminal state, then the process just repeats. Once a model reaches a leaf state, it doesn't have any information about this. So we use our neural network to compute the policy and value of that state. So the policy is used to compute the upper confidence bound, and the value is propagated back up to the parent nodes of that node. Now, if instead the model ends up at a terminal state, so that means that the game has ended, then it just propagates back up the actual value of that state, which is 1 for a win and -1 for a loss. So in the AlphaZero algorithm, they do 800 Monte Carlo tree search simulations per move. So after doing all of these simulations, the model creates a policy based on how often it took a certain action from that root state. Then it samples from this policy to choose an action. All this data, so the state, the policy that it created, And the final result of the game is stored in a tuple. So once the game is ended, the neural network's policy head is trained towards the policy in these tuples, and the value head is trained towards the value. And that's it to the algorithm. So Deepmind says that AlphaZero was able to defeat Stockfish after just 9 hours of training. But wait, they were using Google's Cloud TPUs, which are one of the most powerful pieces of hardware you can get your hands on. Still, it's a pretty big accomplishment for reinforcement learning. Now, the only problem with this algorithm is that it only works for deterministic, fully observable games. So, like, you can use this algorithm to play Minecraft or something. But there are some newer reinforcement learning algorithms that are coming out that can play some really complicated online games, things like OpenAI's DotaBot. Even DeepMind's building a new algorithm that can play StarCraft. And this makes me so excited for the future of reinforcement learning. Like, there's some crazy stuff that's going to be happening soon. Be sure to follow me on Medium to keep up with my articles. The link's down in the description below. All right, see you guys.